Hello, everyone, and welcome back. It's Mr. Hine, and we are back at it, continuing on from where we left off from so many weeks ago at Chapter 5, Section 4.1, where we're going to talk about the chain rule with the fundamental theme of calculus. Now, remember that hopefully if you did the review from Chapter 5, you remember that the chain rule was a derivative rule for when a function is made up of functions, a composite of functions, where it's the derivative of the outside times the derivative, leaving the inside alone, times the derivative of the inside. So that was the chain rule. And now we're going to apply it with the fundamental theorem of calculus, but you probably forget what that is. But don't worry, even if you forgot chain rule, all of this I'll come back to, and we'll go a little bit slow through this, but also kind of quick so you're not spending so long watching this, so you can do your work. Okay, so here we go. So let's recall first what the fundamental theorem of calculus says. And the fundamental theorem of calculus, basically in a nutshell, and there are two formal definitions of it, is it basically said that derivatives and inverses and integrals are inverses of each other. Inverses of each other. The same way addition and subtraction undo each other, the same way multiplication and division undo each other, derivatives and integrals undo each other. They allow us to go forward and back from rate of change to area under the curve. Now, in terms of math language, it would look something like this, where we're talking the derivative with respect to x over the integral from some value a to x, or find the area under the curve from a number to some value x, which we don't know, of a function f of t dt. And remember, the only reason I use t is because I don't want to confuse it with that x. And the idea there is that this just returns the same function f, but in terms of x, right? Where these more or less, cancel each other out because they're inverses, and we're left with the same function just in terms of x here. Now, let's look at a few more recall examples to help you understand this before we jump right into it, because again, this isn't fresh for us. We took time off with this whole quarter system, so I want to make sure we understand this. All right, so the first example I want to look at is, what if it was the integral of f prime of x dx, to help you understand this recall. So what would that look like? Well, we could rewrite that as the integral of the derivative of a function f of x dx. And since the integrals and derivatives are inverses of each other, these more or less cancel each other out, and then we're just left with the function f of x. However, since the integral's on the outside, we're taking the integral last, and since it's an open integral, we have to do plus c. Because again, the idea, if I was to show some steps, is if I work through this, the derivative of f of x would have been f prime of x dx. And then to do an integral, you take the antiderivative, and the antiderivative of f prime is the function such that when you take the derivative of it, you go backwards. So in other words, the antiderivative of f prime is just f of x, but we have to do plus c, because the idea is, again, if we take the derivative of this function, we should go backwards. And when we take the derivative of all of this to check, that would return us to f prime, and the derivative of a constant c goes to 0. And we have to account for that because that's a possible solution. So that's the first one. B, what if you had the example of d dx of 2 to 5 of a function f of t dt? Now, what would that be? Now, just be careful. You might think cancel out, it's f of t, but try to understand this a little bit first before we just go straight to what we think it is. If we're finding the area under the curve from 2 to 5, well, that's a defined region. That's going to give us a number answer, right? If we wanted to do this mathematically, we take the antiderivative of f of t, so we get a function f. So remember, capitalization, as a recall, it means the antiderivative of f. So we take the antiderivative of f, and we're going to evaluate it from 2 to 5. And that's the way we calculate that, and the derivative would have stayed on the outside here. And then we always do upper minus lower, so it would have been antiderivative evaluated at 5 minus the antiderivative evaluated at 2. But these are both just numbers, because if you plug 5 into a function, you plug 2 into a number, those are just numbers, they're constants. And the derivative of a constant is 0. So this one gives us 0 here. And then the last example I'm going to do, part C, is the derivative of a to the x of a function f of dtt. Well, this is actually the fundamental theorem of calculus, which means the derivative and the integral are just going to cancel each other out, and we're just going to be left with the same function f, but in terms of x. All right, there's no plus c here because the derivative was in the outside. And you might be thinking, how is this different than b? Well, remember, 2 to 5 is a definite integral over a known region. So that's actually finding the area under the curve from 2 to 5, which is just a number. But from a to x means you find the area under the curve from a to some value x, which we don't know. So then how can we know our answer? The answer depends on the function and where we're heading. So that's the idea there. Okay. Now, this might confuse this language, so let me just, in other words, show you with numbers to help you understand this. So if the question was the derivative with respect to x of, say, 5 to x of t squared dt, all that means is it's the same function, something squared, but with x plugged in, so it's x squared. So that's what this is saying right here with numbers. Okay, so that's a little recall. And remember, if you have questions on it, please ask, come to office hours. Calculus is tricky, especially on your own in this environment, so definitely I want to be here to help you if you have any questions. All right, let's look at 138, because 138 was the first problem, and that was a problem. If we were in class together, we would have stopped and talked a lot, made sure you understand some of the implications of the work that you're doing. So 138, A was basically saying, in my own words, show that d dx from a to x of f of t dt is going to equal f of x. And I kind of went over it just right now in part C, but I'll do it again because it doesn't hurt for you to see it one more time. All right, so we're going to do it step by step. So if we did it step by step, we do the integral of f of t. So integrals mean you take the antiderivative of the function, and then we're going to evaluate it on those bounds from a to x. And the derivative stays there. We don't touch that. That just comes down. All right. And then we always do upper minus lowers, which is what I was saying. So then this is going to be antiderivative at x minus the antiderivative at a. Right? And the derivative of the antiderivative is just going to become f of x. And the derivative of f of a, well, a is just a number. So by plugging a into an equation, we just get a number. And the derivative of our constant is 0. So then what you end up getting here is just f of x. And there's part A. Now part B was basically saying calculate, and it was going step by step, having to explain it, but I'm going to do it as a problem holistically as a whole. Calculate the derivative of a to g of x of a function f of t dt. And again, just a reminder, because I remember when I was learning this, it always confused me. The only reason it's t and not x here is because we don't want to confuse the x's with this function and with this function, so we just use a different variable. This doesn't have to be x. We could have used t here, but then that would be with respect to t. Just the way, a notational thing in calculus. All right, so what's different with this one versus the last one I just did? It's still going from some number, a, so a is just some number, to some unknown value x. But the way you can think about it is, instead of thinking about it as an unknown value x, think about this as a function. There's a function, y equals x, right? Or better yet, if I write in function notation, f of x equals x. So if we think about it as a function, we could actually write it as like g of x. Now what's going to happen if you use g of x and we just stick with that notation rather than x? What happens? All right, same thing I just did. So we take the antiderivative, which is f of t, and we determine it from a to now this function g of x. And all of this is getting the derivative. All right, so that's just how we calculate integrals using the fundamental theorem of calculus, is that we can do the antiderivatives. And then we do the upper minus lower, so then you have the derivative of the antiderivative at g of x, where you just plug that in, minus the antiderivative at a, where you plug that in. And now we're taking the derivative of this. So the derivative of this, notice you have a function of functions, which is the chain rule. So what's that say again? My chance to reiterate those words to you. The derivative of the outside, so the derivative of the antiderivative of f is just f, leaving the inside alone, times the derivative of the inside. There you go. And then we have the derivative of f of a, but that's just a constant, so that's going to go to 0. So what all this becomes is this is actually equal to f of g of x times g prime of x. And that's actually how you calculate the chain rule. Now, as a side note, the reason I never said that previously, why we never did that when you first learned this, is if I went back to A, when I did the derivative of fx, I technically could do the chain rule. I would do, side note, you could do chain rule. You could do the chain rule here, where it would be the derivative of the antiderivative f, which is just f, leaving the inside alone, times the derivative of x. Well, what's the derivative of x? The derivative of x is just 1. And notice because it's times 1, it doesn't change anything. It's still f of x. And that's why it always worked. But that is, it can actually be any function there. It doesn't have to be x. All right. So in general, I think part C, and then I'm going to show you 2 examples and wrap this up. Part C was saying, in general, if you have a function d dx from some constant to some function g of x of f of t dt, well, that's going to equal the same, because the derivative integrals cancel each other out, it's still the same function f, but it's at g of x. But since we're doing the derivative, and this is a function of functions, it's the chain rule where you saw here, it's the derivative of the outside, leaving the inside alone, but it's not f prime here because, again, these cancel each other out. So it's the same function f, leaving the inside alone, times the derivative of the inside, which is g prime of x. All right. And furthermore, if the bottom was a function too, so say it was h of x to g of x of a function f of t dt, well, what that would equal is it's the same function f, because the derivatives and integrals cancel each other out, evaluated at g of x, but then we have to do the derivative of the inside there, minus, well, you would have had to plug in h of x, which is what would have been here. Like this would have been h of x, and we'll plug that in as the lower bound subtracted it, which is f of h of x, leaving that alone, times the derivative of that, which is h prime of x. So you just got to remember, if you plug it in, and I know I got squished, oops, take the derivative of the inside because of the chain rule. Now let's look at examples to help you. All right. So I'm going to leave that there. No, I'm not. Let's just go to a brand new page, because that way you have a whole screen to look at. All right, brand new page. Well, no, I changed my mind again. No, I changed my mind again. Here we go. Let's look at examples of how this works, which is what your work is really about, and knowing how to do this skill in a way. All right, we're going to look at 2 examples. The first one is the derivative with respect to x of the integral from 5 to x to the third of cosine of t squared dt. All right. So the idea is you don't actually have to do the integral of cosine of t squared, because since we're doing the derivatives, you're going to cancel each other out. So you're still at the same function cosine, because of the idea that derivative and integrals cancel. But instead of looking at t, we evaluate it at x to the third. So that's x to the third squared. Drawing mechanical pencils. And we wouldn't do 5 because the derivative constant, it goes to 0. But you have to take the derivative of x to the third. So times the derivative of the inside, which is there. Excuse my dog. I guess the male is here or something, and that's okay. So simplifying this, what you get is cosine of x to the 6th times 3x squared would be the derivative of that. And then you can always bring those in front as the nicest way of writing it. And there's the answer to this problem. Okay. And let's look at one more. And I think with this one, I think you should have an idea of how to do all of these. So we have the derivative, but now the lower bound is also a function x squared, cosecant of x. Now, I don't like calling it function. I know the book does that because technically 5 is a function. But remember, if I would have used 5, what's the derivative of 5? The derivative of 5 is just 0, which makes it go away, which is why we don't include it. So I guess you still could have applied it, but that's okay. We'll just keep going from where we're at. Of t to the third minus 1 dt. Right? So we don't have to do the antiderivative of this because we're doing the derivative, and that's going to cancel it out. So we're going to still be at the same function, which is root. And instead of t, we're evaluating at the upper function, which is cosecant of x to the third minus 1. But we have to do, since we did the derivative on the outside, we have to take the derivative of the inside. And this is just a reminder of the derivatives of your inverse functions. And again, this is something that you want. I think as you do it more, you will memorize. But I do have this memorized. The derivative of cosecant is negative cosecant. Sorry, I got confused in my head for a second. Cosecant x cotangent x. So that's the derivative of cosecant x. And then it's minus, man, I should have done this on a new line. This is ugly. New line. I don't want to confuse you. Start over. The derivative of x squared. I'm so rushed. X squared to cosecant of x of root t to the third minus 1 dt. Where are we at? You keep the same function. So it's root. And instead of t, you evaluate the upper cosecant of x to the third minus 1. Doesn't look too nice the way I wrote that. All of that thing. And then times the derivative of the inside. The derivative of cosecant x is negative cosecant x cotangent x. And then we do minus, because again, this would have been the integral, how it's the upper minus the lower bound, minus the same function. But instead of t, we evaluate x squared. So it's x squared to the third minus 1 times the derivative of the inside, and the derivative of x squared is 2x. And there's your answer right there. And that is the right answer, but we want to make it look nicer. So anything that's timesing, you can put in front of the root there. So I can write negative cosecant x cotangent x, root cosecant to the third of x, just another way of writing to the third, minus 1, minus 2x, root x to the sixth, minus 1. And there's your answer there. So the idea is the fundamental thing about calculus, how derivatives and integrals cancel each other out, is great. And that helps us with not being able to having to do the antiderivative. We can just keep the same function. However, if you're valuing it as an actual function, which I guess you always are, you just have to consider the chain rule. Well, after you plug it in, leave it the inside alone, but then take the derivative of the inside. Okay. Now, if you're still confused, that's totally okay. Just stop by office hours, send me over an email, reach out to some people in class, and I'm more than happy to. And I'm sure the people in class will understand, so I'm more than happy to help you. All right. Good luck on this.